All right. Oh, wow, that was wicked. All right. Welcome to section 85A, algebra. And this is the first part of the second half of chapter 8. And really, we're going to be talking about factoring here for the rest of the way. Section 85A, using the distributive property. And basically what this is just we're going to start in factoring, and really the rest of the chapter is all about factoring. And so if you have to write this down on a spot in your notes or somewhere, that everything we talk about here is going to be involving factoring. And what factoring is, it's kind of the backwards way of doing FOIL and using the distributive property. It's probably working in reverse, working backwards. And that's kind of what factoring is. And another way of putting it is, like, we've been multiplying polynomials. This is kind of the way we divide them. It's kind of working backwards, so the backwards of multiplication is division, and that's kind of what we're working on here. So today we're going to start the basics of it. We're going to talk about prime factorization and greatest common factor of integers and monomials, and then we're going to factor out two-term expressions. So we got a lot to do today. So this is a large section of notes, so hopefully we're ready to roll. So let's first talk about a prime number. What a prime number is, it's any whole number that's greater than 1, whose only factors are 1 and itself. We've heard of prime numbers before, but that's it. All you have is 1 and another number. That's the only things that factor. Factors are numbers that multiply to make that number. So, for instance, an example would be 17. My favorite number, as you guys know. 17. The only numbers that you can multiply to get to 17 are 1 times 17. And another one would be, say, 37. 37, again, the only numbers that multiply to make 37 are 1 times 37. A composite number, what is a composite number? Well, this one is any whole number greater than 1 that has more than 2 factors. I should just put that has, not 2 or more, but I should just say that has more than 2. More than 2 factors, okay? So any whole number greater than 1 that has more than 2 factors. So some examples here would be like the number 4, okay? Because you could multiply 1 times 4. You could also multiply 2 times 2, so you have 4 factors there. Or the number 12. Or the number 12, okay? And because we've got to think about when we talk about composite numbers, when 2 or more numbers are multiplied, each of the numbers is called a factor. Okay. So what would the factors of 12 be? We know, in that one we can go. If we look at 12, well, you could say 1 times 12 would give you 12. We also know that 2 times 6 would give you 12, and then 3 times 4. So that's definitely a composite number because it has 6 factors: 1, 12, 2, 6, and 3, 4. So factors are the numbers that you're multiplying to get that. Okay? So next up, let's talk about some practice problems here. Factor each number, then classify each number as prime or composite. So we look at, say, A, number 22. What can we do? How can we multiply to get to 22? So I usually start at one end with 1, and then I come way over here to the right to say, well, 1 times 22. And then I'm going to kind of write numbers in between. So I know 1 and 22 work. And then is there any other numbers that we can multiply to make 22? Well, 2 and 11 would make it, right? 2 times 11 is 22. And that's it. That's all there is. So because there's more than 2, we know that this is a composite number. Okay. For B, 31, well, we know right off the bat that 1 and 31 multiplied by each other would give you 31. But is there any other numbers that you can multiply to get to 31? And they have to be whole numbers. They have to be integers. They can't be decimals or fractions. And so no, the answer is no, you can't. So this would be a prime number because the only 2 factors are 1 and itself, 1 and 31. 1 and 31. Okay, so that brings us to the next part, for prime factorization. When a number is expressed, I'll give you what that means first. I'll put the definition up there for you. When a number is expressed as the product of all prime numbers. Okay, so what that means, we're going to break down the number, and eventually you're going to have all prime numbers that multiply to give you this number. Okay, so the first thing you want to do is make a factor tree. Okay, make a factor tree, and we'll show you how to do that. And then for a monomial, you're going to make a factor tree and then write out all the variables. So when we actually have variables involved, we're going to write those out as well. So we can just get to practice on those right now and say, all right, what is find the prime factorization of negative 132 times x squared y squared? Okay, so the first thing I'm going to do is I'm going to just kind of separate the variables right now. I'm just going to leave those and just go with negative 132. Okay, so let's take a look at this negative 132. And we're going to make a factor tree, and then we're going to, okay, again, that's what that said here, right? So we're going to make a factor tree. Just backing up here. And then we'll deal with the variables later. So let's make a factor tree here on 132. Now, just because we know it's negative, right off the bat, I know that I'm going to have a negative 1 times something here, okay? And what's the negative 1 times? It's times a 132, okay? But I can still break down that 132 further. So there's a couple different ways in which you could get to 132, but I'm going to use 11 times 12. And so you might just have to guess and check and figure out certain numbers here. But the easiest way is to find something that's multiplied by a prime number. Now, because I know 11 is prime, I'm in good shape. Once I find my prime numbers, I'm going to go ahead and circle them. So I know negative 1 is prime, because I can't break that down any further. I know 11 is prime, so I'm going to circle that. 12 is not prime. So there's a couple different ways to get to 12. You could go 3 times 4. You could go 12 times 1. 2 times 6, whatever. But I'm going to go 2 times 6 just because I know that 2, again, is a prime number. It doesn't matter. If you went 3 times 4 here, you're going to eventually get the same result. You're going to get the same result eventually. I just went 2 times 6 because I know 2 is a prime number. And then finally, I can break down 6 into 2 times 3. And I have 2 more prime numbers here. Okay? So now I'm going to list them as in terms of prime numbers. And I'm going to go in order from lowest to biggest. So I'm going to start here with negative 1. All the numbers I have circled here, basically. Here, 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 and here. It didn't matter, like I said, if you went 3 times 4 for this 12 here, if you went 3 times 4, you'd have your 3 prime number, and then you'd have a 4 that you'd have to break down into 2 2s anyways, so you'd still get the same answer. But so let's write these down in order from smallest to greatest. So negative 1 times 2 times 2 times 3 times 11. So we have all of our numbers, negative 1, 2, 2, 3, and 11. Okay, so all of those are prime numbers that multiply to make negative 132. Then we have to deal with the variables now. And it's okay, we can deal with those. We just have to write those out. Okay? We just have to write those out here. And we know how to do that. X squared becomes x times x, right? And then y squared would be y times y times y. So we made a factor tree for the number and got all our prime factorization right here. And then because it was a monomial, we actually wrote out the variables xx and yyyy. Okay? All right. The next example here, we're going to find the prime factorization of 84. And we're going to do a couple of these together, and we're going to answer question C. So let's look at 84 first. Okay? So let's go here with part A of 84. So again, what we have to do is we're going to break this, make a factor tree. And so we can think of different numbers that multiply to make 84. And here's where your calculator is going to help you to just divide things evenly. But I got 4 and 21. Neither of those are prime because they can break down even further. But 4 breaks down to 2 times 2, which those are both prime numbers. So I'm good there. And 21 breaks down to, let's go back to red here. 21 breaks down to 7 times 3. And those are both prime numbers. So we're in good shape here on 84. So when we write that out for 84, we're looking at from least to greatest, we would go 2 times 2 times 3 times 7. Okay? Now let's look at 30. Let's go with 30 here and see what we can have if we have any differences. So let's go ahead and make a factor tree. And again, you could do multiple ways here. Some of you guys are going to go 3 times 10 right away. That's fine. And then you're going to have to factor tree number 10. I'm going to go 6 times 5 because it's just the first thing that came to my mind. 5 I know is prime, so I can circle that. And then I'm going to go 6 is 3 times 2. And those are both prime as well. So it really doesn't matter how you did it, because even if you went 10 times 3, you'd have your 3 as a prime, and 10 breaks down to 5 times 2, so you'd have all these numbers anyways. So our numbers for a prime factorization of 30 would be then 2 times 3 times 5. Okay? Now our next question then is, what is the largest number that is a factor of both 84 and 30? So the easiest way to do this is, sure, you might just know this and be able to guess and check in your calculator, but let's take a look at both of the prime factorizations and see if they have any in common. And they do. Okay? We have a 2 here. They both have a 2, and they both have a 3. So because they are both in common, we can say that 2, whoa, I don't like that at all. We can say that 2 times 3, because they both have a 2 and they both have a 3, we could say that 2 times 3 would be the greatest factor, the largest one, which is 6. So both 6 would go both into 84 and 30 evenly. It would be a large factor, and that would be what we call the greatest common factor, or GCF. The greatest common factor would be 6 in this case. Okay? So let's talk more about greatest common factors then. Greatest common factor. We also call it GCF. We're going to kind of say that a lot. So GCF is our shortened term for it. All right, it's the greatest number and or variable, or variables, that is a factor of the given numbers. So the largest one that's a factor of any number that's given to you. And the way we are going to find this is write the prime factorization, which we just did, for each term, and circle the common factors. And then we want to multiply those, just like we did here. We circled the common factors 2, right here, 2. We circled the common factors 3. We multiplied them here, and that gave us our greatest common factor. That will work for you all the time. Okay? So going back to that now, let's look at number 4. Find the greatest common factor of 12 and 18. So let's go ahead and do that. So if I look at 12, if I just factor those out, I'm going to go 2 times 6. And we've got 2 is prime. And then 6 is going to be 2 times 3. And those are both prime. So we're in good shape. So for 12, I'm looking at 2 times 2 times 3. Okay, and then 18, if I go with 18, I'm going to go, say, 3 times 6. Again, there's multiple ways to do this, but any way you do it, you're going to get, is going to be factored down to prime. And we talked about 3 being prime, and then we've got 2 times 3 here, and those are both prime. So for 18, it was really 2 times 3 times 3. Okay, so now we have to look at, do we have common factors in our prime factorization? Yeah, we've got 2's here, and we've got 3's here. So again, we can say 2 times 3 equals 6. So 6 is our GCF. It's not always going to be 6. It just kind of worked out in these 2 examples that it was 6. All right? Okay, remember the distributive property. So let's work on that now. And now we're going to kind of work in the opposite direction. So we've got the distributive property, and now we're going to kind of go backwards. All right? We know that if we were to do this problem here, if we distributed, we'd get 5x times 3 is 15x. And then if we went 5x times 5x, we'd get 25x squared. Okay? I know we would get that. All right? So in this case, what we're doing is we're going to kind of work backwards here. When we factor these things, we're going to say, and today only, binomials. Today will be binomials today. And here's the steps we're going to take. We're going to take these steps. We're going to find the GCF of the terms, the greatest common factor. And remember, that could be a number or a variable, or both. A number and or variables here. It could be either one. Number and or variables, right? And then we're going to write the GCF on the outside of the parentheses. So in our example up here, this 5x is actually our GCF. It's the greatest common factor in both the terms, 15x and 25x squared. And we were able to write on the outside, okay, GCF. You'll see more when we do other examples. Then we're going to divide each term by the greatest common factor and write each result inside the parentheses. And that's basically our leftovers, okay? Okay, so you're going to take that, find the GCF, and you're going to take the number and or the variables, and then they're going to put that on the outside, and then your leftovers kind of go on the inside of the parentheses. And that's how we factor polynomials. And today it's just going to be binomials. So let's take a look at this example here. Okay? So this first one, 15x plus 25x squared. That's a good one because this is kind of the example we did here. This should be your answer, 5x times 3 plus 5x. Okay? So the one thing we want to do is we want to find out our greatest common factor. Now, if you can go ahead and divide this, and you know, I tell you to go ahead and do that. That's going to save you some time because you don't have to do prime factorization every time. So if you know right off the bat that 5x goes into both 15x and 25x squared, then great. Then you're in great shape, and you can just kind of go ahead and do that. But let's say we don't know. Let's say we don't know. Then I'm going to give you a tool that will always work. So I'm going to go find the greatest common factor. So with 15x, how does that break down? Well, I know that 3 times 5 would give us 15, and then I'd have an x here. So 3 times 5 times x would be prime factorization of that first term. How about the second term? The second term, 25x squared, would be a 5 times a 5. Those are both prime numbers. And then we'd have an x times an x because we have x squared. Right? So now we have to kind of look at what is the common factors that both these have. Well, they both have a 5 here, and they both have an x here, so our GCF would be 5 times x. Okay? So I can take the GCF. Now our rules state over here that we want to put our GCF, find a GCF, then write the GCF on the outside of the parentheses. So that's what we're going to do. Write it on the outside of the parentheses. So 5x here is going to go on the outside of the parentheses. And then whatever's left over is going to go on the inside of the parentheses. So prime factorization is really nice because once you do that, you found the GCF, you put it on the outside. Now you divide the GCF and you get the leftovers. So if you're really good at that, and you know you can pull out 5x, well then you can divide it into 15x, go for it. If not, look at what's left over. We have a 3 right here, so we can put that in there. And then we have a 5 times x in the second one. It would be 3 plus 5x would be our factor. Okay? And you can work backwards to see if it works out, but 5x times 3 is 15x. 5x times 5x is 25x squared, so we know that we're correct. But again, if you can go ahead and divide right off the bat and see this binomial here and say, hey, I know just because I'm good number sense and I'm a good smart enough math student to say, hey, I know that 5 goes into both of these and so does x, then 5x is my greatest common factor. Then go for it. And then you could just say 5x times what equals 15x? 5x times 3. So that 3 would go here, and 5x times what would give you 25x squared? 5x. So if you're able to do that, by all means, go for it. It's going to save you a little bit of time, and you should be in good shape for it. If not, then use this up here, this prime factorization chart, because this makes it pretty easy. Once you find your GCF of 5x, that goes on the outside, and then whatever's left over. The top one, you've got a 3, and the bottom one, you've got a 5 times an x, and that gives you your answer. So let's look at number 7 then, just to make sure that we've got this one going. Okay? Let's make sure. So in this case, I'm going to do some work over on the right here for this one. We've got 12a squared plus 16a. So if you can figure out what the greatest common factor is without doing prime factorization, please do, because that'll save you some. But I'm going to do it for those that don't know how to do it. I'm going to say, okay, let's take a look at that first one, 12a squared. 12a squared. How do I break that down? All right, well, I know that it would be, if I had to make a tree, I'd end up getting, what, 2 times 2 times 3, right? Because if I go 12, break that down, 6 times 2, and then 2 times 3. So it would be 2 times 2 times 3. And then I have the 2 a's, so I have to go multiply a times a, right? And the second term there, the 25x squared, we'll do that in green here. Not 25x squared, sorry. The second term here, which is 16a, okay, 16a is actually going to be 2 times 2 times 2 times 2 times 1a. Okay, because remember, if you broke down 16, it would be 4 times 4, and 2, 2, and 2, and 2. So you'd have that going on for you. All right? So, and then we have the a to add. So now we look at what are the greatest common factors here. Well, we have a 2 for sure that matches up. We've got another set of 2's that matches up. And then we've got this 3 and 2 doesn't match up, the a's, but we do have an a that matches up here. So now if we multiply those to find our GCF, and we're going to multiply all the common terms. So it would be 2 times 2 times a, right? 2 times 2 times a. So our greatest common factor here would be 4a. 4a. And like I said, you may have been able to figure that out already. So 4a is the GCF, goes on the outside. Now we kind of divide into these terms, do some division to figure that out. And you'd get, 3a here. And then we divide into the 16a, and you'd get a 4. Okay? Now let's double check that over here, because we had our GCF on the outside. And now let's look what we put on the inside. The leftovers go on the inside. So 3 times a, 3a. That's put right there. And over here down in the second term, we got 2 times 2, which gives us the 4 here. So your GCF goes here on the outside of the parentheses, and then your leftovers go in here inside the parentheses. All right? Last one here. Let's look at number 9. Why? We've got this first term, 2a times 6a plus 8 is not in factored form, where 4a times 3a plus 4 is factored. Why is that? Why is that? Okay, the biggest thing here we have to look at is, if we take a look at this one, they did not use the greatest common factor. They used a common factor, for sure. They used a common factor with 2a, because 2a does go into both of those, but they could have went further. And the reason I know that is because you can look and say, these can still be divided by something else. So they could have went to another level. So they did not use the greatest common factor. So you kind of have to look for those things to make sure we're using the greatest common factor. Okay. I know that was a lot to it, but that's the beginning of factoring. Every section from here on out to the end of the chapter is going to be on factoring. So how will you find the GCF? So will you write it out in prime factorization, or will you just think of factors and try to divide it yourself? How are you going to be able to do that? That's what I want to know. And then let's make sure we do this practice problem to get us going there. I want to factor 18xy squared minus 24x squared y. So again, find your greatest common factor first. If you have to make a prime factorization table, do it, because it'll help you. But other than that, we'll look at it some more and answer some questions. Okay? I know it was a lot today, but bring any questions and we'll be ready to roll.